Okay, welcome everybody on yet another talk on the today's Java Path on the Java conference. And I have a pleasure to uh, present you Jake Luciani, who is chief architect in the data stacks, people behind the Cassandra. You have already seen Jonathan Ellis' talk. It was wonderful. I expect exactly the same kind of show, Jake. So the mic is yours, the stage is yours, and I'm turning myself off. Have fun.
All right, thank you very much, Archer. Hi, I'm Jake Luciani. I'm a chief architect at DataStax, where I help build our Astra DB cloud database built on top of Apache Cassandra. So some of you may have seen Jonathan's talk a couple talks ago. Yeah, so we worked together, and I helped a bit on the JVector. Jlama is my personal project, and it's basically about my interest in transformers and large language models, and trying to understand how they work, and how to bring that sort of new sort of world into the Java ecosystem. So the agenda today, we'll give a brief introduction, talk about like what are LLMs, why do they matter more and more for us, especially at work. I'll give a brief introduction on Jlama's features and a quick demo, talk a bit about how these things work internally, and then finish up with some practical examples of how to use Jlama in your code base. All right, so as I mentioned, I've been working at DataStax for a number of years. Before that, I actually studied cognitive science and computer science in school. Unfortunately, I was very interested in AI, but I was a bit too early. So I'm super excited about like what's happened in the past couple of years. It's finally a chance to dive into the interests that kind of drove me to programming in the first place. Like how do these things work? Like how can we make computers more like brains? And in general, things are sort of turning true, and LLMs are being used more and more at work, and I think that's an interesting transition. It's gone from sort of like toys and fun to like actually this is going to change what we do. So I don't think we're going to be replaced by Gen AI, but I do think it's a new paradigm that all of us need to kind of understand, and it's a tool that we can use. And so the picture on the left is a quote from Andre Karpathy, who helped start OpenAI, and I thought this was funny that it's not Rust, it's not Go, it's not Python. The new programming language is language itself. And it's interesting and true, but as I mentioned, it's not the kind of thing that is gonna that's all you need to do, but it certainly gives you a new chance of talking to your program, and telling it what you want it to do to kind of help you run the applications that you're building. On the right here, this is 2023 to 2024. You see that that AI adoption is growing. I'm sure that all of you who work in enterprises are hearing more and more of this, and this is why, especially for Java developers, I think it's important for us to have tools to kind of use this, take advantage of it. So most people are used to using AI and LLMs in terms of talking to ChatGPT or using Gemini or all of the different Gen AI services out there. But what's really interesting to me is being able to run these things locally, because they're not just for chatting or asking asking for help with a coding problem. You can actually embed them in your existing or new applications to be able to extend them to do things that they couldn't do before. And the great thing about local LLMs is, they're obviously secure, and most of the good ones are open source. So they're free to use, which is really what makes this new paradigm interesting for us as developers. You can actually own and control and understand where these things are, what they are, what data they're keeping track of. So in terms of like what these LLMs can do is, you can actually use them to execute your existing code. So instead of just having a text bot text box that you can chat with, you can actually tell it, here's my existing Java application. Here's the API I want you to call, and when I ask you to, call that function, take the output, and do XYZ with it. So the next big thing to talk about, and this is I found this interesting chart on the right here that sort of shows that the size of the LLM matters in terms of how smart it is, but for many of the applications for local LLMs, you don't need someone with a huge IQ and all of the world's knowledge kind of help you parse dates, for example. So what this chart shows is, up to 30 to 40 billion parameters. The model's intelligence starts to trail off. So the really big models, the O1 and GPT-4 are like huge and massive, and you need these all of these GPUs and spend a whole lot of money to run them. But for most small applications, you don't need a gigantic model. And some of the things that they can do is just classify text. It can say, like, this text is spam, it's not spam, this is a positive tweet or a negative phrase. It can, as I mentioned, call your tools, and it can summarize text, and it can do data processing. So so sort of small language models are what Jlama is kind of built for, even though it can do large ones too. And finally, why does this matter for Java? The AI revolution has kind of been in Python, and C and C++. And I think that's great and all, but for us running enterprise Java, it's still used widely across most companies. So most developers know Java. They want to use Java. So, having to switch, between like, okay, I'm going to write this in Rust, I'm going to write this in Go, I'm going to write this in Python, I'm going to write this in Java. As interesting as that is for us developers, when you're trying to run a company and trying to maintain a large code base, choosing one language helps, keep that debt, low. So this chart shows, that Python and Java are now like the number one and number two language. But I would argue that most of the back-end software, most of the things where Java shines, is data management. A lot of you probably use Kafka or OpenSearch or Elasticsearch or Spark or Cassandra. Your data lives in Java. It's managed by Java. Your LLMs and your data should be as close together as possible, because the LLMs, work off of your data. This is why projects like Jvector and Jlama are so important. So what is this toolkit for Java developers? As I mentioned, there's Jlama for the actual LLM inference. There's Jvector for vector search of your data, which is all built in Java, and LangChain for J is the kind of abstraction on top, which allows you to easily implement APIs that work with LLMs externally or internally. All right, so so what is Jlama? So Jlama is a pure Java engine for running inference on these large language models. It's built using JDK20 and up, because it uses the Panama vector API. It's fully integrated with LangChain for J. So that you can do tool calls, you can build agents, you can do vector search, etc. It excels at doing classification, embeddings, tool calling, and just text to text chatting. It also includes a open AI compatible REST API if you want to run a model externally, and it can be clustered across your existing hardware if you want to do inference across those large models. So there's really no limit on how small or how big they can go. So I want to give a quick demo on Jlama. So to install it, it's quite simple. You basically can just use JBang. So there's basically a CLI tool, which allows you to interact and download models. So with JBang, you can just do JBang app install Jlama at tjake. So there, I just installed it, even though it was already installed. I can now list which models I've downloaded. I've already done this ahead of time. And there's a bunch of models that I have on my, there's a bunch of models I have on my Hugging Face, which are quantized for Jlama. But these models can, but also just the base models can also be run It supports, like the Jlama models and Llama 1, 2, and 3. Mistral, Granite, Quen, Yecoder. There's like a whole bunch of models that it can run. So I'm just going to pick one here, and if I just do Jlama chat, and then I'm going to pick this one. I'm on a Mac, so I got to remember the shortcuts. So basically, I could just start chatting with it and say hi, and it can say hi. What can I do? Like say, tell me a joke about Python. So it can just make things up. I can do tell me another joke, and you can see for these models, they're quite fast, and they're just running locally. So that's sort of the basic interaction with the chat API. So I wanted to go into how these things work. So these LLMs are actually quite simple. Most of the work is done on the training side. So you need these 100,000 GPU clusters to kind of train these things, but to actually run the inference, you don't need that much hardware. And the way it works is it's kind of these stacked layers of these transformer blocks on the left here. So a model might have 20 layers. Each of those layers is one of these blocks, and they have multiple parts to them. There's a attention mechanism. There's basically residual connections to the results of that, and there's just a basic feed forward network. So what happens is you basically pass a input set of tokens, and each of those goes through what's happening on the right here, which is basically your tokens are converted to a vector, and that vector is passed and transformed from layer to layer, and the output vector represents a set of probabilities of what the next token is. So you generate the next token and you feed that back into it. So it's kind of this like recursive loop where it just goes like from your input tokens and then it keeps generating the next token. You append it to the set of tokens and it goes to the next one and so on and so forth. So the inference is, that's what inference is. So it's not super complicated from a sort of conceptual standpoint. Now, in terms of the details of it, there's a lot more that goes on here. The models, as I mentioned, usually live on Hugging Face. That's kind of the GitHub for open source models. There's the model format itself. What these things are basically sets of matrices which map directly to these layers. And for each particular piece here, there's matrices associated with the attention layers, the normalization layers, the feed forward layers, etc. So for each of those layers, you have a bunch of matrices, and those need mapped and loaded into memory, and there needs to be a tensor API to kind of do things with those matrices. So the next bit is tokenization. When you send it a phrase, you're not sending the raw words in. As I mentioned, every token is mapped to a vector. So every word is broken into a set of tokens. So it depending on the model, they're kind of trained on a particular set, particular vocabulary. That vocabulary maps to a vector for each of those tokens, and that's the input to the LLM forward pass, which is what I'm showing here on the right. So the forward pass is the, how you get to the next token. So you're forward passing through all those layers and going back out and looping back in. So that's tokenizers. There's multiple types of tokenizers. So there's model formats, tokenizers, there's the model themselves. There's also prompt templates, because the way these LLMs are trained is they basically do self-supervised. There's three parts of model training. There's a self-supervised phase where they just run for months on all the internet on all of the internet, plus all books, all data sources that folks can find, and they self-supervise, learn how to complete missing tokens from that gigantic data set. That's where most of the compute goes in these in the model training. What that does is it allows the model to generate sort of features about the data itself, and depending on how many layers the model has, the more layers it has, the more it can generalize and understand what the conceptual meaning of all those tokens in token order mean. So the attention mechanism plus the training itself allows it to derive from these raw token sets into like what the relationships between things. And this is where like all the magic happens. The second part of it is called fine tuning, and that's where these prompt templates come in. So for each of these models, if you just talk to a raw model, it wouldn't know what to say. It would just do what it did during its training phase and just try to complete what you asked it. But it doesn't really know what you're asking. So these prompt templates sort of fine tune it in order to complete a question and answer type interaction. So the data set gets much smaller, and you're training it on like, here's a math problem. What's the answer? And the format of that prompt is the same for all question types. So this is how you're able to make the model more usable, and this is where where all the real magic happens. This is kind of the missing piece. The last part of what you need is a sampler, because for each of those forward passes, what comes out the other end isn't the next token. It's a set of probabilities of all of the tokens in the vocabulary, and what the percentage likelihood of the next token being. So so there's multiple ways to do it. You can basically do a top K and choose a random one. You can always pick the highest one. You can sort of make sure that you don't repick the same token over and over. So you can help steer, what the output is. And this is often what's referred to as the temperature. So the temperature of the output, you're basically telling it how random of an output do you want, or how constrained of an output do you want. So a temperature of 0 means it will always output the highest, the next most likely token, and a temperature of 0.5 will also will basically allow you to pick from the top n in a random fashion. So that's kind of a bit of a deep dive in terms of how these models work. And this is kind of why I wanted to build Jlama, because I really wanted to understand like what's involved here. Because I think it's important as developers, we're going to start using these things. So it kind of helps to get a sense of at least what's going on. Now, in terms of what the model's doing internally in these forward passes is something that no one really understands yet. There's a whole field called mechanistic interpretability, where they're trying to decode layer to layer, like where concepts are kind of mapped into these layers of vectors and matrices. But it's definitely a brand new field, and they're starting to get some results. But this is kind of the future of being able to get more control over what these models are doing. All right, so in terms of just raw developers, this is what is the fun part, is how do we make these things go fast? Now, on the right, here's a flame graph of basically a forward pass. And what you're seeing is that most of the time is spent, 90% of the time is spent just doing matrix multiplication. So like nothing else really matters in terms of performance other than making these matrix multiplications as fast as possible. Now what's happening is you're basically taking your input vector and you're doing a matrix multiplication against the trained weights. So you're basically taking one token is represented as one vector. That vector changes as it gets passed through the layers. But at the end of the day, you're just doing matrix multiplication after matrix multiplication. So how can we make these things fast? Over here on the left is basically a matrix multiplication in just naive Java, and very easy to read. It runs, but the problem is it's not going to be super fast, because these, as I mentioned back in the earlier slides, these models can have billions of parameters. Each of those parameters is effectively a float inside of a matrix. So if you're doing a forward pass on a 30 billion parameter model, you're effectively doing 30 billion multiplications. So it's a lot of data that needs to get pushed through the CPU. This is where vectorizing helps a lot. Vectorizing is SIMD, which stands for single instruction multiple data. This means instead of doing one multiplication at a time, you can load a set of floats into a CPU register and multiply all of them at once. So over here on the right is the same code, just rewritten using the new Java vector API. And what's great about this is the same code will run on different types of SIMD. There's, I think I showed here. Every CPU has a set of flags. Those flags include what type of SIMD they have. On this particular CPU, I don't know if you could see my cursor, but there's AVX512. So that means the registers are 512 bits, which is 16 32-bit floats. And each core has those registers, and obviously your computer has multiple cores. So effectively, you're turning your CPU. Your CPU is kind of a mini GPU. So GPU, all it does is SIMD. It doesn't do anything else. So the only thing it can do are these math instructions, and they just have so many cores and so many registers that you can do SIMD across tens of thousands of cores on one GPU versus 16 cores or 32 cores or whatever you have on your laptop. But the effect of this is, you can get a large jump. I think this is like an 8x jump in terms of performance just on one CPU by doing this using the vectorized API. So you're just cutting down the number of instructions that need to happen. So it seems like that's all you really need to make it fast. Unfortunately, the problem is, and I think Jonathan alluded to this on the JVector, is really the bottleneck isn't the compute itself. It's also the memory bandwidth. and I think I show this on the next slide. I'll jump here real quick. So the memory bandwidth is really the limitation here. As I mentioned, if you have a 30 billion parameter model, you need to get 30 billion floats to the CPU as fast as possible. And unfortunately, Moore's law didn't apply to memory. So the memory bandwidth grew 7% year over year versus like CPU performance grows, you know, in the Moore's law effect. So the problem is you might have lots of compute, but if you can't get the data to it fast enough, then it doesn't really matter. This is where quantization comes in. And what this really is you take those 32-bit floats and you can break them down into more lossy floats. So instead of like pi out to, out to 16 decimal places, you can instead do like 8 or 4 decimal places or 2 decimal places, or even the smallest quantization I think is 1.5 bits per float. And the reason why this works is these models during that sort of base training phase, the features that they extract from the data are very strongly represented. So like, even if you change the weights so that they're no longer quite the same, the pattern of those weights in the matrix stays intact. So what it means is, you give up some accuracy, but your performance shoots way up. And I thought a great way of showing what quantization is visually. The photos on the left-hand column are all the same resolution, and on the right-hand column they're different types of quantization where you're losing some detail from the photo. Like here, you could still see the mountain on the lowest one, but you can't really make out the clouds. In the second one and third one, on the middle and top, you really can't make out the details, but you still know what it's a picture of. And that's kind of what the features are that the LLM has inside of it. So even though you lose detail, you can still get the gist of it. Okay, let's see how I'm doing on time. I'm running out of time. So let me just jump to my demos. So let's see. I've got 2 things I wanted to show. One is how you write the code to basically do a function call. So here's a function call which gets a number of GitHub stars. And what this does is it allows you to, it just does a REST call, right? And here's the code to basically say like, hey, I've built this tool and I want you to use that tool as part of your conversation. If I go here and run that, so I can say like, how many stars does Gjik Jlama have? And then it's going to go off in the background. I show it on the slide here what's happening underneath the thing, but there it says 699 stars. So it got the live data because it's using the function call. This could be a function inside of your existing set of applications, and LangChain for J makes it really easy with some annotations to basically wrap those functions. And the last one I wanted to show is a pretty useful thing. Like, so let's say, for example, you are doing you're building a web app, and there's sort of an open field that someone left in there. You have all this data of like people entered dates manually. Now, if I said to you as part of an interview, write a function to parse all these dates correctly, you would probably, I mean, that's a really hard problem. So if you run this by itself, well, so basically what I have here is the naive version, which is using the datetime format builder. And even with a bunch of different templates, it only gets about 5 out of 20 correct. But if I do the same thing, but I just change the model, I just changed the method to actually tell an LLM, like, hey, the user is going to send you a date. For example, here's an example, and you must return just the formatted date in this format. And if I run this, you'll see it. It uses the model to extract the correct date. It still gets some wrong, but it gets like 90% of them correct. And
wonderful.
I think that's all. Yep.
Yeah. Thank you very much, Jake. Sorry for stepping up, showing up, because we need to end the presentation. It was great. It was as I expected. We were talking about the proxy CPUs, themes, things like that. Very good talk. We do not have time for questions. However, if anybody wants to ask some questions, we probably can reach out to you on one of the social media. Which one you prefer? If you are fine with the questions as well, of course.
Yeah, on X or Twitter or my GitHub project themselves, there's a discussion section. There's also a link to a Discord.
Okay, wonderful. Thank you very much. It was a pleasure to have you here.
Thank you.